Okay, so I just finished the Revision 5 prototype board for the Sol BLE Tracker, and I'm really excited because you can see the charge current is extremely steady. All the leakage current that I had before, gone. Or there's no leak on the reference capacitor, so there's no drop here. Now, I was having a huge problem with it. I couldn't measure the resistance. It was clearly too high, plus the capacitance throws off the measurement. So I couldn't measure the resistance from the capacitor to ground or wherever it was leaking. But after giving it a reflow under my IR station, it is rock solid. We have no problems here. The other issue I had was that I put the wrong low dropout regulator on there, and that was sucking 170 microamps in quiescent current when it was operating. And this one I put on there is a 500 nanoamp quiescent current one, worst case 1.3 microamps quiescent current. And it is charging from the solar cell from the light from my microscope. This is so awesome. So let me show you some zoomed in views now. Okay, so you can see it's charging at 317 microamps. I want to show you what happens when I put it into the shade. So you can see as I start to occlude it, dropping, and if I totally cover it, we're only drawing 1.5 microamps on average right now. So the only thing missing from the system is the Bluetooth low energy module, and that's supposed to draw an average of about 10 microamps plus 1.5 microamps quiescent. So its RF pulses are averaged out to about 10 microamps, and its quiescent is about 1.6 microamps. So we should be drawing less than 14 microamps when we have it running. Okay, so I'm just doing a test with my microscope light, which you can vary. You can see I got the lux meter on the Galaxy S3 running. And I'm going to see how much charge current I get at different lux readings. So right now, at full brightness at this height with the light distance, we're getting about 1600 lux, and that is giving us about 58 microamps of charge current. So that's about 5 times what we need to run the system at 1600 lux. And now we're just going to bring it down in increments of about 100. So you can see the reading's still bouncing a little bit. Seems like in these lower light levels it moves a bit more right now, but we're doing much better than we were with the other board. So I will bring it down to 1500. Right, the only thing to keep in mind is all these measurements were done under white LEDs, so the response of the solar panel is probably different under sunlight. So I will repeat this in different light levels in the house, ambient lighting, direct sun lighting, and check what the lux meter thinks those lightings are, and I'll see how those compare to these measurements. But these should give us a pretty good idea of what kind of performance we'll see. So you can see the data I took outside and around the house. It's sorted by lux and current. You can see there's this huge dip here. I'm not sure exactly what the cause of that was. It might be the angle of incidence between the lux meter and the solar panel wasn't quite right. But obviously there's this general correlation.
and we can get some general ideas. So, basement pool table, sunny. Of course, there's the deck, so that includes a lot of the light. So we have very few lux, and we're losing power. And then the bedroom with the blinds closed, very few lux, still losing power. Then we get to this chair that's sitting in the loft, but the back of the chair is facing the window, so we're not getting much power. And there's the kiddie bed in my sister's room, and the blinds were mostly closed, but it's still got 140 lux in there, and that's 6.2 microamps we're getting, so that's almost enough to charge. And you can see these measurements are fairly consistent so far. We're not going to get to the major inconsistencies till we get into the huge numbers. I think maybe this one was just a bit off. This backyard container one. Because in the shade we seem to get a lot of lux on the meter, but not that much power. And then in a totally different spot, in the direct sun, we read a low lux but more power. I think that was just angle of incidence, because the phone was tilted towards the sun in the shade in the case of the backyard one, and in the case of the container one, it was just aimed up towards the deck. So I think this is just an angle of incidence error here. It's going to be more like, realistically, it's going to be more of a curve like that, and I'm doing with the mouse. Alright, back to the lower readings. So, kitchen table, still not enough power to power the device. In previous tests, I had gotten 17 microamps, so this is a low reading. Must just be the conditions. Then on the couch in the TV room, the back of the couch, we're getting enough energy to power the system, and that's the place the cats like to hang out, so that's pretty good. So here we go, 2 more kitchen table readings at different times during the day. So this one maybe was just something funky going on. Now the loft by the window, I don't see the cats there very often, but that's 3 times system power. Now this, the front couch, the cats do like to hang out here. And that's good, because that gets the most sun. That's on the south side of the house, so the sun faces that way. And this is in the shaded part. Usually the tree is shading it, or some other part of the house, or it's just at too much of an angle, and we still get 7 times what we need in the shade. But of course, you can see the front couch here again. We can get direct sun, and then we get 56 times what we need, which is good. And you can see the highest we got, I aimed it at the sun, out in the backyard, no clouds, and we charged at 3.3 milliamps. So angle of incidence does matter a bit, especially with direct sunlight. Okay, so this is the light data from the microscope light controlled test. A few things to point out. First of all, this jump here, that's the one I had to reposition the light so I could get the higher energy data. With the light at the height it was initially, I could only get about 1600 lux. Then I moved it a lot closer and I could get 25,000 lux. But unfortunately, the price to pay for that was this discrepancy. The first interesting thing to note is the initial data has a slope of 25 lux per microamp. So you can see here, you can see that in the data here, it goes down 4 microamps for every 100 lux. So that means for every 25 lux, we get another microamp of power. Now that would be more of a slope like this. And I assume this has something to do with angle of incidence, I'm not sure, but then as we increase the power, when I reposition the light closer so I can get higher lux levels, we end up with a slope of 42 lux for every 1 microamp. I just thought this data would be interesting to look at, so we can kind of figure on how many lux we would need to power it. So at our figure of 25 lux, so here's another thing, of course at the lower end it doesn't hold. We have to be up in the hundreds. So after the first 100, you can see we've only jumped from, negative 1.5 to 1.5. So that's about 3 microamps. So that's actually almost fitting with the curve. It's not quite, but just a little bit low. You could probably chalk that up to noise. So even in the low end, it seems like it does hold that 4 microamps per 100 lux figure, which then, as we can see in the data, which means to power the device, we have to consider the quiescent current of the power system, which is 1.5, and then add that on top of our system power of about 10 microamps, so we're looking at 12 microamps, so you would figure around 300 lux, but we don't quite get there. So you can see the slope's not quite high enough. So this is the first 100 lux. That jumps us 3. The next jump jumps us another 3, and then the next jump jumps us a little more than 3. So it's not quite as linear at the bottom. Anyway, so 400 lux is about the level from the white light that we're seeing that would give us enough system power. And if we go back to the old chart, 400 lux, you can see we're actually getting enough at 200 lux. So it looks like it absorbs a lot more from sunlight than it does from the white light.